We started to seriously do testing at the Energy Research Center of the Netherlands, where I worked at that time, to for a technology that's called TORWASH. I invented it about 10 years earlier for upgrading biomass to fuels. And it is a hydrothermal treatment. And for the non-technical people, hydrothermal treatment means that you treat something in water at a high temperature, above 100 degrees, but because you keep it in a confined space in an autoclave, that the pressure rises. And with the increasing pressure, the boiling point goes up. So we treat it typically at 200 degrees and at about 10 to 20 bar. That's that prevents the water from boiling, but it makes a lot of chemical reactions possible that at ambient pressure cannot be done because the water starts to boil. It changes the chemistry of fuels, of grass, but it fries them. It's like you make the same things as you fry things in oil, makes it brown and brittle. There were two business cases that were particularly interesting at that point, which one is the sewage sludge. And this is what we started our company off. Well, you have to pay money to get rid of it. By treating it with TORWASH, you can remove nearly all the water from it. And since sludge is 90% water, you reduce the volume, you reduce the amount, the mass, and you can save an enormous cost on disposal. That was the disposal costs. A few years later, just for the fun of it, I have put nearly every type of biomass in the autoclave test equipment. One of my colleagues asked, well, here is the wrapper of the National Geographic. It's made of bioplastics, so it's biomass. What does it do in your equipment? I said, I have no idea, really no clue. Let's try it. So on Friday afternoon, literally a Friday afternoon experiment, we just put it in one of small autoclave of 100 milliliters, heated it up to 200 degrees, opened it afterwards after cooling down, and it found it's completely gone. It's fully dissolved. And analysis said it's a lactic acid solution. And that triggered, that started the whole application of TORWASH to plastics, because we found out that it is the biodegradable plastics that are sensitive to this treatment. Polyethylene, polypropylene, PVC, polystyrene, it doesn't do a thing. Even PET, it shrinks, but it's not depolymerized. And depolymerized means that of all the small molecules that you have made a chain of, you cut them one back to the original molecules. And that's what TORWASH does with polylactic acid, PLA, and PHA, and a few others, exactly like a bacterium would do it, but just a lot faster. So you treat it at about 200 degrees for half an hour, and it's all back. Well, that was so interesting that once we founded the company for sewage sludge, and we have made a test installation for 1 ton per hour, that we thought, well, let's try to do the same trick, try to do the same scale up for bioplastics, because there is no chemical process for recycling of bioplastics. There's mechanical recycling, and you can digest it back to biogas, or it can be composted. So it's rather safe, but there's no chemical recycling. And well, chemical recycling, bringing it back to its own original monomers, to the original molecules, and then resynthesize it. That is true recycling. That is actually going back to exactly where you started from, and not a useful application somewhere down the road. And if this is possible, and if this can be done in chemical reactors, you can scale it up like the chemical industry. And you don't need bioreactors and this could be a breakthrough for the application of PLA. Well, let's start with PLA, but the other ones are included. That this is a great way for us to have a new and independent source of lactic acid that's not coming from food. And you avoid the discussion that you need food or corn or sugars to start with. You make it just from your own waste. So you do not incinerate, you do not put it in a compost where it just goes back to CO2 and water, and the bacteria have well, they just use it as if you and I were eating sugar, so it doesn't add anything useful. But you can now recycle it truly. At lab scale, I've done hundreds of experiments. After 4 years of small scale experiments, I know exactly how PLA and PHA behave on a chemical level and how they interact with all kinds of contaminants. I've done that in my time at the Energy Research Center of the Netherlands, when it was taken over by TNO, and now as TORWASH, I run we are only a 3-people company, but I run the lab. I have a few students working for me, and we do tests now primarily on plastics or with objects, where people say, well, this is a PLA bottle. Can you recycle it? And I say, well, let's try it. The philosophy of this project is that in 5 or 10 years from now, there will be a lot of PLA and PHA in the mixed waste plastics. These are all kind of wrappers or foils or objects, bottles, cups, whatever. They need to be removed from the other plastics. And I brought in my network of my collection of companies, including Avantium and Arapa and Pax Biomaterial, Corbion and Total Energy Corbion, as a whole. And that's the Dutch hub now within this project. And since I started it, they say, well, it's a natural thing that you will be the hub leader. Even though we are only a very small company, we have not developed technology for plastics recycling beyond the lab, but we have a big ambition and we have an experience with upscaling this for sludge. And plastic is easier than sludge, I can tell you that. We just accept contaminations. We know it's going to be there. We will have a contaminated stream of water and of lactic acid, and we have a good connection or combination with Corbion, where they do the purification with the known technology. They have 50 years of experience in cleaning up lactic acids. And we've done a few tests, a few projects together with TNO and with them to verify that the type of contaminations that comes from our process can be handled by Corbion, and they can. It's just a matter of a level. How clean can you get it? How much acetic acid can you accept? Acetic acid is a decomposition product from biomass. Also with phenol and furfural. These three, you should, well, if you listen to the tape, so acetic acid, furfural, and phenol. They come from biomass, from wood, from paper, and they contaminate the stream of lactic acid. They can all be removed if you accept that the stuff is dirty. And that makes our process or our projected process different from the rest. It's absolutely necessary to have this technology on a larger scale, on a full scale, for a breakthrough of biodegradables. And innovation is that we will not do this only on lab scale with clean or well-controlled materials, but with materials that come from recycling, that contain all the contaminants, and how to deal with these. The project is about scaling up. So we do not expect in this project fundamental innovations, but practical innovations. And this is, for instance, if there are steel wires in it, how do we remove them? If we have how are the other plastics, because we cannot never have 99% purity. We will have 90 or maybe even 80% PLA, and the rest is something else. How does this behave in a pressure cooker, and this is the innovation we are seeking, how can we modify our reactor and the operation of our reactor so that we can deal with these contaminants? Sand and glass sink to the bottom, and soil. Polyethylene and polypropylene rise because they're lighter. So we need to invent something to suck out or this polyethylene and to remove the other ones. Oh, let's include also nylon and PET, the solid pieces that sink, and make this a true continuous operation. Because the reactor stops when we have fed so much PLA that the contaminations of the top reach the contaminants of the bottom. At the end of the project, we want to have we have proven that at a 1 cubic meter scale, we can turn PLA into lactic acid. We can prove our process on a 1 cubic meter scale, because that is the last step before full scale.